Welcome, everyone. I hope you're not tired, but really awake, got your shot of caffeine, some sleep last night, and are ready to learn about how graph databases make your life a better place. And of course, also how to develop applications with a graph database like Neo4j or Spring Data Neo4j for that matter. First, some organizational stuff. So you all got this book. Feel free to read it. It's really good. I reviewed it. And it's an easy read, and it's a gentle introduction to graph databases. So I can really recommend that. And if you are local or are in the area anyway in October, there's a $99 ticket for our Graph Connect conference in San Francisco in your book. And feel free to drop by, but it's also possible for you to come to New York or London if you want to. We will do a meetup tomorrow evening around 6. So it's just around the corner. So if you want to join, feel free to come for some wine and beer and some nice food. And actually, I brought a signed copy of the Spring Data book, signed by the Spring Data project leads. And if you want to win it, then you can drop by and perhaps get this copy. So that's more or less the organizational things. First, I want to ask about you. You're probably awake, I hope so at least. Got some coffee, got some sleep, you got a book and a ticket, so that's all set. I assume you use Spring because you're at Spring 1. Something I want to ask you, who of you uses a NoSQL database in his daily work and life? So that's about 20% or so, 30%? OK, who of you has used the graph database or Neo4j for that matter? OK, cool. So that's really good, because then my intro part of the presentation is not in vain. So you can actually learn something from that. Something about me. My name is Michael. I've been with Neo4j for 4 or 5 years now. And I work in all the parts of the company. But my main tasks are the Spring integration and taking care of our developer community, which is growing every day. And every day, more of my time is spent answering questions, helping people, and getting them to rock. But I also do lots of other stuff. So you can ask me anything about Neo4j. It's not limited to just Spring Data Neo4j or something. Agenda for today. Oh, by the way, I will try to stick in my booth here because there are so many traps here, and I don't want to trip or rip my computer off the desk. So please don't be angry at me for that. So today I want to speak about connected data, graph databases in general, and Neo4j. A bit about Spring Data Neo4j, give a short introduction, show you a very small example app, which is a Twitter app. But not the usual Twitter app, where you kind of rebuild Twitter, but you consume Twitter data and derive some insights from that. And then I want to talk about some real-world customer and use cases. That's a bit a tricky part, because it's not so easy to share openly most of the customers, domains and code and so on. So I had to work around that. And then summary and Q&A. For everyone who came late, I don't mind being interrupted with questions. So if you have any questions, feel free to ask. So let's get started. NoSQL. So some of you used, yeah? I'll upload it to the Spring 1 slide. NoSQL databases. So some of you already use NoSQL databases. I assume everyone else uses relational database. NoSQL is not just about alternatives to relational databases or using many different databases together. It's about some trends in data that we've seen. So we've seen that the size of data grows. The amount of data that's produced every year grows exponentially. The kind of structuredness of data kind of gets less and less. So we get more and more heterogeneous data. And we have more and more data that's actually heavily interconnected. I'll show some real-world use cases for that, or real-world examples for that, and all of them make up the kind of data complexity. So most of the NoSQL databases deal with the size and semi-structure problem. Graph databases deal with the connectedness problem. So we'll focus on this part today. In general, NoSQL doesn't stand for no to SQL, but it stands for not only SQL. So if I list NoSQL databases, there are also relational databases down there. And we have all the other types, key value databases, document databases like MongoDB, column stores like Cassandra, relational databases, you know them, and graph databases like Neo4j. So, and actually, the NoSQL movement is kind of an evil movement to developers because it moves or puts much more burden on all of you. Because nowadays, we have this decision to make. I have an application that deals with a certain set of data, has to solve several use cases, and I as developer, or we as a team, have to decide which databases should we use for the different use cases, for the different types of data. And so to make this decision, we have to be informed or knowledgeable about what the different databases are good at, how they scale, how they deal with complex data, how much operational costs do they have, how do they fit in our technology stack, and so on. So kind of a lot of burden was moved towards the developers from the one-size-fits-all paradigm of the past to you have to choose, and it's polyglot persistent, and NoSQL is much about choice. Right? You have to consciously choose with the knowledge that you have which databases you want to use to build your application in the best way possible. And that's why all the stuff is there, and all of them have different attributes. If you look at the two major dimensions, which is size and complexity, then we can see that all the aggregate-based databases like key value stores, column stores, and document databases, which are the first three, which have this kind of concept of an aggregate, which is shardable, but atomically in its own, really deal well with high volumes, have some problems dealing with connected data, so it's really hard to cross-reference information in an aggregate-oriented database. Relational databases have this notion of foreign keys or foreign key relationships, so they are somehow good at modeling relationships. They're not so good at dealing with them in the real world. Every one of you who has seen a SQL query with 20 joins or something like that and saw the performance of the SQL database that came out of that knows what I'm talking about. I experienced it in the past, so I felt the pain. And graph databases are better at the complexity, especially at the not just modeling the complexity, but also dealing with the complexity during the application runtime. And both relational databases and graph databases still deal very well with the volume that's usually needed. So most companies, most corporations don't have the Facebook or Twitter or Google problem, right? So you don't have to have trillion of entities or exabytes of data, right? So most of the companies just deal with normal-sized data sets, enterprise data sets, which are easily handleable by both relational databases and graph databases as well. There, the aspect of fast development, ease of modeling is much more important than dealing with the size of data. To take a step back and look at the data we are dealing with on a daily basis, I want to pose the questions, aren't graphs everywhere? So if you look at the real life, things we deal with are things we have learned, things we have experienced, and so on. So everything is connected. We are connected to the people in our family. We are connected to places from our past. We are connected to events. The same is true for history. The same is true for politics. The same is true for economies and markets. There's so many factors that kind of create these intricate networks of relationships in a, for instance, economic market, or in ecology, or in biology, or in physics. So everywhere you look, if you look at the big picture, at the whole picture, it's not just the entity or the elements that are important. The relationship between them are as important as the entities themselves. So, and usually what we had a problem with in the past is that we want to actually keep this rich relationship in our data. and we don't want to dump down our data just to fit it in a database, because then we lose valuable information that we then later on don't have available when we want to answer questions, right? So if we get a question that is really intricate, that would explore certain relationships of our data, but we had to dump it down to fit it in a schema, and then all these relationships are gone, so we don't have any means of answering these questions. So we know that all the big companies work on graph-based solutions, from Facebook, Open Graph, Facebook Graph Search, to Google's Knowledge Graph, to Twitter's Interest Graph. Pinterest wrote a blog post about their graph model lately. Netflix has a graph model for recommendations. Amazon has graph models for recommendations. So all the big companies just build their own stuff. They have enough troops to just build their own, and huge in-memory clusters of terabytes of RAM. But usually you want to just use an off-the-shelf solution to get stuff done. And you don't command like 1,000 engineers or 10,000 engineers to build a universal graph database for you. So you use something off the shelf, which could be, for instance, Neo4j. So the most obvious use case of graph databases that we've seen so far is social networks. People are connected with each other. You want to follow each other. You want to see other people's interests, places they've been at. You want to get recommendations for locations. You want to do all these things, right? And then, as for instance, with Facebook with Facebook Graph Search, it also enables you to search in a natural language way over this accumulated graph data, which is really interesting. Impact analysis is another really interesting topic. So one use case is networks. So everyone, like, for instance, Cisco, who sets up huge data centers with thousands of switches and firewalls and racks and all that stuff. They want to actually know when this firewall breaks down, which part of the data center is affected. Do we have alternate paths? When this server fails, do we have backups for that? What happens if we get an attack on this part of our network? How can we deal with that? So kind of figuring out the first level, but also the second and third level impacts of, for instance, damages or changes are really important. Another thing of impact analysis is, for instance, software analytics. So you can easily model your projects as graphs, all the classes that are related with each other. You can also model inter-project dependencies, like you, for instance, can see with Maven the dependency graph in Maven. And other aspects like that as well. For instance, software metrics and so on. And there you also do a kind of impact analysis. So if I want to change this class, which parts of my system are affected? What do I have to retest? What do I have to look for? And so on. So this kind of transitive impact analysis is really important in lots of areas. Another obvious use case is route finding. So from public transport to cross-transport route finding. So you don't want to do just planes or just trains, but you want to go from A to B across a number of different means of transport. That's something also done frequently with graph databases. And something that's really nice is that those databases also support graph algorithms, like finding shortest paths and so on. So you don't have to go on and implement all the stuff on your own, but it's kind of coming out of the box. Also really helpful. As I already mentioned, things like recommendations at Amazon, at Spotify, at Pinterest, at Twitter, at Prismatic or so. All these recommendations come from somewhere, right? So they record all your data, but without tracing who bought what and which categories are these things in, and finding people that are similar to you. So actually, you don't want to get recommendations from your, like your grandmother or something like that, right? So you want to get recommendations that are relevant for you, and not just for the business, right? Of course, they want to make money and sell you stuff, but they also don't want to annoy you. If they give you really wrong or bad recommendations too often, you just go away and go somewhere else. So what they want to find people that are similar to you, right? So for us, it's similar nerds and geeks, right? So they trace our buying behavior. They find kind of the demographic that's similar to us, And then they look, what other stuff did the other guys buy or were interested in or did really like? And then it's just a simple graph traversal problem to recommend something to your customers. Logistics is another interesting example that kind of relates to route finding. It's a bit more involved because the performance requirements are much higher. So for instance, a customer of ours is a huge European logistics provider, and they route 2,000 to 3,000 parcels a second. So they calculate 2,000 to 3,000 routes per second every day or every hour of the day on a Neo4j cluster. So kind of to deal with the modern shipment that came actually from all these recommendations and online buying stuff. To route all of them, you have to have a system that's able to sustain high rates of pathfinding as well.
So how big was this cluster?
This was a 6-machine cluster.
Like how many nodes, how many relationships?
Oh, they have, I think, 5 million nodes or so. 5 million nodes and I think 100 million relationships or something like that. So it's not so complex, not so big, the graph, but the kind of performance requirements that they have to find so many paths in a short time is really the big challenge there. Access control is another interesting question. Usually access control is boring. No one wants to deal with that. And when people want to have to deal with that, they kind of get hit by this. You know, we have trees of access rights. We have groups which are contained in other groups, and then we have positive and negative permissions, and we have to resolve all of this stuff. And usually it just blows up and takes a lot of time to resolve permissions. And in the graph, it's just finding the person that wants to log in and follow the path to the actually, for instance, objects or services he wants to or she wants to access, and then just see on the path if there's any denial on the path, and if there's none, they can just access it. So it's kind of a millisecond decision making instead of seconds or minutes that you otherwise can get. And another interesting use case is fraud analysis. So from everything from financial services to insurances to just shops, or I have later an example of a game company who sells games, and they have lots of problems with fraud. You duplicate US keys and email addresses and bulk purchases and all the stuff. It's also easier to find these things. For instance, there was a bank in Europe which took all their 10-year transaction data out of the mainframe, extracted the interesting parts of this data, projected all of that into a graph, and then they tried to find circles, kind of cycles in the graph. And money flowed from one person to the next, to the next, to the next, over 6 steps or more, and then ended up at the same person again. Or the same people were involved in the same kind of money transfers all the time. These kind of patterns that you can find in the graph indicate fraud, and then you can drill down to the raw data and do more detailed analytics on top of that. This kind of pattern matching is also interesting in other parts. For instance, in biology, if you look at proteins and gene sequences and things like that, there the scientists also want to identify certain patterns that are interesting to them. And of course, the graph doesn't contain all the raw data that comes from the gene sequence, which is also kind of terabytes of data or so every day. But they want to see the higher level picture. They want to see, like a human looks at patterns and find patterns. They want to create a graph, find the patterns. And then with these patterns, they can still drill down to the raw data and do the more detailed analytics afterwards. So it's more the ad hoc, real-time queryability of the graph database that helps them there to make decisions. And there are many more places. So even in things like art, the whole topic of internet services and so on. So actually, we find these connected structures everywhere. And more people are realizing that it's really a good way to just take your model that looks like this on a whiteboard and put it into your database, and then in the database be really able to follow these relationships, to leverage the connections between your data, and then derive more interesting values out of that. OK, graph databases. We all know relational databases, right? No surprises there. So we have tables. So in this case, we have a customer table and an account table. And if you want to join them, so one customer can have many accounts, one account can have many owners. We need a join table in between, right? In any reasonably complex domain model, you probably don't have just one join table, but a bunch of them. And so whenever you want to find these connections between customer and its accounts, you have to do 2 joins. And if you want to do more complex queries, they add up. And the interesting thing in a relational database and also other NoSQL databases is that you have to compute the relationships at query time. So in every database where you just have a foreign key ID to some other table, like from the join table to the entity tables, you have to compute that at query time. So you can use indexes and all the stuff. But at query time, you have to match the IDs. You have to pull it all into RAM and have to compute these connections. And in a graph database, this looks different. So if we compare that directly with a graph database, we have the same red customer here. We have the blue accounts here, and the relationships are directly entities in the database. So they are really structures in the database. So the connections are not just one ID there and one ID there, and which have to be joined somehow, but they are really instance level connections. So this customer really has an instance connection to this account and to this account and to this account. And so what a graph database does is just a cheap trick after all. They just pre-serialize these relationships at insertion time. So they don't want to have the costs at query time. So what do? You pre-materialize or create this information. And then at query time, a graph database doesn't have to compute any relationships. They just have to follow them. So it's just like pointer chasing. I start here. I know the next place I have to go. I know the next place, and so on. So it's a kind of constant time operation that you can do in a graph. In a property graph like Neo4j, we call these things nodes, and the connections in between relationships. And the interesting thing is, unlike mathematical graph models, that's not the end, but you can put any number of properties on both nodes and relationships. So you can really have rich domain objects as nodes, and you can have rich relationships with time information, with weights, with quality information, with comments, remarks, things like that, in between the elements. You can have also multiple relationships between 2 nodes and multiple relationships of the same type of different types. It's all up to you how you want to model your domain and which kind of use cases you want to support and have to support. And for navigating this graph, you have to start somewhere. So in a graph database, what you usually do is local queries. So you have something to start with, either a person, a place, a product, a song, an artist, something like that. And if you have found the starting point, it's just following these relationships to find the information that's interesting to you, to aggregate it and project it to some result and be done. And to find the starting points, we use indexes. In Neo4j, it's by default Lucene. You can also plug in other indexing solutions. But just to look something up by name or by ID or by something else, then we can use these indexes. Yes?
So can you go to the previous slide? So in your experience, is the performance of GraphDB more a function of number of nodes or the relationships?
It's a function of the depth of the traversal. So interestingly, the graph database is not affected by the total size, because as you do local operations on the data, so you just start somewhere and you locally follow some relationships. So imagine I want to ask my graph database something about the people in this room, right? It doesn't matter how many people live in the US or in the world, right? If I only want to do this local information querying, then only this tiny piece of the puzzle is interesting for me. And it's the same with graph databases. So if you do the typical graph searches, the total size of the graph database is irrelevant. So you don't need that. But the number of hops that you take, that is kind of linearly affecting your performance.
But in case of
Hmm?
at the end?
It's still, you start, you can also start at 2 points, by the way. So you can start at 2 points and start do at the same time traverse things until you get the first intersection. And then you kind of narrow down from, so this gives you the first estimate of the route. And then you can narrow down this route within a few steps as well. So it's also just 2 points and you follow the paths. And there might be, if it's the route finding is just for Germany, where I'm from, the rest of Europe and the world might be completely irrelevant for that. You just need the stuff that's relevant for your current query scope. And that determines the performance that you. Okay.
How do you find out first starting point?
They usually come from the domain. So, for instance, for a recommendation, you are the logged-in user, right? So you start with you, or with the product you're just looking at. Or in the logistics example, you have sender and receiver of the parcel or the package, right? So you know the places where it has to go from and to. So all these starting points come from the domain. Like you say, I want to compute I want to compute the impact of this router failing. So you have this router as starting point. So you always come from the domain with the starting points. Okay. How would you query this graph database? So Neo4j itself, as the 4j indicates, back in the time like 10 years ago, the 4j was quite hip. So when Neo4j was founded, they added this 4j suffix. Nowadays, it's not so hip anymore. So we'll see what happens with that. So in the beginning, Neo4j was all just Java APIs. It ran in your process, in your JVM, as an embedded database. And it was all kind of low-level Java APIs where you dealt with nodes and relationships directly as objects, and you could follow relationships from nodes and so on. And the point is, this only scales so much, and is also so much appealing to non-Java developers and non-JVM developers. They usually don't want to deal with Java. And also, most people don't really want to learn a new API to deal with database. So what we started out is to create our own query language, which is tailored first to readability and secondly to deal with the concepts of a graph. So this query language is called Cypher. So as you probably can infer from the name Neo and Cypher, so Neo4j is much inspired from the Matrix movies, because our founders were really fond of the Matrix movies, especially the first one. And so lots of these names went into the database. So this query language, the most interesting part of this query language Cypher is this match clause, because it defines patterns that you want to look for in the graph. And what it actually does, it uses an ASCII art syntax. So if you look at these, all the things in parentheses are kind of round things, and all the others are just ASCII art arrows with dash dash greater than or less than. And so if I showed this part of the query to someone from the business domain, they can easily see what it's about, right? Because a user actually see the arrow is in the wrong direction. I put it not in by intent, but this arrow is in the wrong direction, right? Something like this could be easily spotted. An account contains booking, and then you have recipients, and then you can aggregate the recipients and get the kind of top 10 recipients of your database. So that's the way that you create that. So you start at a person, and then you just follow the relationships as implied by this pattern that you give here. And then as you do that, you accumulate information, you aggregate information, and project the results. And this query language is both usable from Neo4j Java APIs as well as Neo4j server, so you can use it from any language like, JavaScript, Ruby, Python, Erlang, Haskell, and also other JVM languages as well. A more involved example of that is I want to find people with the same skills. So in a relational way, I do the select from the users and join on the skill table. So it's a kind of self-join. And in the graph database, I say, OK, I started a user, and I just match this single relationship between users and skills, and get the skills back and the relationships itself as well. For instance, the relationship could store how well or how good I am at the thing. For instance, I'm really good at Java and graph databases, and I totally suck at web design, right? So something like that. Graph databases in general are also whiteboard friendly. So what you do is you just grab a colleague or someone who knows the domain, grab a whiteboard, get a coffee or a Coke or something like that, start to draw your domain as you want to. Yes?
So I have a question about using indexes. So you showed a query previously, so how the indexes can be used there?
Yeah.
So do we have indexes on relations also, or?
Yeah. OK. So the question was, how do indexes relate to the query? So in this case, we have an explicit manual index. It's called user here. And what we do with the starting clause is we say, OK, we start at this user node, which comes from the user index, and the key that we look up is name. It could also be something like email or login. And the value is Andreas in this case. So that's the way how to interact with these indexes. There are also indexes on relationships, but they are not really important for everyday use. Because what you do in a graph is just follow relationships. You don't look up relationships by an index, but you look up entities, nodes, and then start to go from there. There's changes a bit with Neo4j 2.0. I probably won't go into that, but we have lots of material on that and at the conference, and also tutorials about that. Indexes in the graph database are not really used for speeding up queries. That's the big difference to relational databases. The indexes are really just kind of lookup or catalogs, right, where I can find information, and then from there on I go into the graph. In a relational database, you would use indexes instead to speed up queries, to minimize the number of elements that the database has to look up on for joining, for instance, or for finding values. So the whiteboard friendliness, it's we just grab someone who knows the stuff we want to deal with. The use case is the domain. We draw it on a whiteboard. And then when we're done, then we are kind of done, right? So because if you put that information in the database, you can't read it that well. But it's the same people with the same nodes relationship. So that's a visualization directly out of the database. So the data that you model on a whiteboard and data that ends up in a database has the same shape and structure. So you can easily map each to each other. So you can talk to a domain person on this level, and then you can show them the results of your queries or the results of your graph modeling, and it looks the same in a real database. So it's much easier to grok for them and to understand and reason about. And then they will probably go there and point out that there are, for instance, relationships missing or attributes missing, and then you can go for the constructive discussions. Neo4j itself as a database, as a graph database, as I said, it's a schema-free graph database. So like most of the other NoSQL databases, Neo4j is also schema-free. So that really helps with a quick and rapid development cycle, because you don't have to change a schema every time you add some kind of information. Something that's also important is that a relationship in a graph database is much more like data. It's not like a structural thing like in a schema in a relational database, but it's like data. So if I add a connection from me to you, to all of you, for instance, it's just like setting a name in a column or something like that. It's not implies, OK, I have to add now something in the schema that allows me to add those relationships to this person, but I just do it, right? So, and if I come up with a use case that needs a different type of relationship, then I just add these kinds of relationship. And also, if I don't have this kind of relationship, this kind of connection on a certain entity, then you know what? Then the application code has to deal with that, because it's optional. It's not enforced, so you don't have to have the same kind of structure everywhere, because that's not like the world, what the world looks like, right? So the world is really different, and all the people are different, all the things we deal with are different, and so why should we kind of align them in a single structure as well? Interestingly, graph databases are more like relational databases in terms of transactions. So most of the other NoSQL databases have this. Yeah.
So when you are trying to model like in graph database, you are more like so if I do comparison between relational databases and this one, relational databases are more like you are trying to design a class kind of thing. Here it is an object instance.
Yeah.
Is that true?
Yeah, that's one of the aspects. You can treat it as an object instance, and then depending on your context that you're currently working in, you can project this object instance to different roles, kind of, or different classes, right? So you can have the same, for instance, person node, and this person can be a citizen in one case, it could be an employee in the next case, it could be a developer in the next case, and it could be, for instance, father and husband and in the next context, right? So it's the same node, the same entity, but it has many different roles, and it's much easier to project it to one of these different roles, where in each of the different contexts, other attributes and other relationships are important, right? So my kids, for instance, are not really important in my employee role, right? Except for calculating some, salary or something like that. But in general, you have different attributes that you look at, and it's not all the same. And then this kind of projection ability that you project elements to a different role in a different context is really powerful. In general, what's really funny actually is if you look at entity relationship diagrams, they are actually graphs and graph models. So we start with a really nice model of our domain in a relation database, and then we throw all the information in between away and just look at tables in the end, right? So we have a much richer model when we deal with relational databases at the beginning when we model, and then we lose lots of this information by just sticking to the single table per entity model and lose all the other information as well. Okay. Most of the other NoSQL databases have this aggregate concept. So key value stores, document databases, column stores, where you have atomic operation within the aggregate. So if you update something, all the updates within a document, for instance, in a document database are atomic. But if you update, for instance, in MongoDB, a DB ref, so the other document doesn't have to be there. So there's no guarantee that you have a consistent view of the world after your operation is finished or half finished or something like that. And graph databases are more like relational databases in this regard because they have a really fine-grained data model. So the nodes and relationships are really fine-grained. And actually in a graph database, you also tend to normalize much more than in a relational database because connections, joins kind of, are cheap. So joins are not expensive. So you're encouraged to normalize more, to pull out attributes, for instance, into separate nodes and then connect other nodes to the same attribute because it also enables or makes it much easier to do things like matching. One interesting use case is dating sites for graph databases, dating sites and job search, because you have to match people with profiles via attributes. And if you pull out the attributes as nodes, it's really easy because you have two people or you have one person. You just follow his or her attributes, and then you see which other people are connected to these attributes, and then you just rank them by the quality or the information you have about their attributes. And so this really fine-grained data model also implies that it's really dangerous to update it just like that, because if you just do it like that, then you most certainly get up a corrupted data model because only half of your data is updated. You have a few relationships were added, but none of the properties or the other way around. And if you want to update or add, for instance, a more complex subgraph or substructure to your database, then you end up with messed up data. And that's why graph databases also use transactions, which also has the nice benefit that they can interact with other transactional databases. So you can set up, if you want to, XA, two-phase commit, global transaction things. If you want to have the updates in your relation database and graph database occur either at once or don't occur at all. So that's, especially in the context of Spring Framework, enterprise applications, and so on, asset transactions are quite helpful. And it really helps you not to mess up your data, which is also often quite helpful. People don't like when we mess up business people's data. I don't know why. And it's really fast because so it's implemented with its own storage engine. So in graph databases, differ by the way how they are implemented. Some of the graph databases sit on top of another database and just add a kind of a graph layer on top of that. Then you have to do the mapping between the two models and kind of take care of that. In something like Neo4j, it's custom storage down to the disk. So we have our own store formats, our own storage files, own storage layer, memory mapping layer, and all this stuff. So it's graph constructs, so it's nodes and relationships down to the disk level. So you can even, if you look at the database directory, you have a nodes file and relationship files and property files and so on. So it manages its own storage as well, and that allows it to really be really fast with a huge number of traversals, relationship hops per second. And as I already mentioned before, you can either run it as part of your JVM process, so you can run it in your web app, you can run it in your Swing app. So we have, for instance, HP uses Neo4j for telecommunications monitoring software, which runs as a Swing app, and they have just embedded Neo4j in this app, which they sell to telecommunication providers. And yes, it's embedded, but many others, like for instance, Adobe has set up a global cluster of Neo4j servers around the world at AWS to serve their Creative Cloud. So both deployment modes have their interesting pros and cons. And Neo4j has a cluster, as I already mentioned, for read scaling and high availability. So this is the same information as a graph. And the different modes of operation, of course, have implications on which languages you can use it from. So most of the non-JVM languages use Neo4j Server, and the JVM languages either use Neo4j Server or Neo4j Embedded. So I already spoke about Cypher. I don't think I have to repeat it. Yeah?
So does Neo4j provide something like for backup and restore?
Yeah, so Neo4j comes in several editions, and the Enterprise Edition provides clustering, backup, online backup, and so on.
That's where the database is adopted like backup.
Yeah, exactly. So you can do online backups while the cluster is running or while the database is running. You just point it to another database or directory, and it backs up the data there. And it also can do incremental backups, so either full backups or incremental backups and so on. So as it's transactional, it kind of, the backup works like that. It's a transactional database, so it provides transaction logs on commit, and it just uses the transaction logs on backup to transfer the transaction state onto another database. So it can do the delta updates onto previous states to get faster to the current state in the backup database. And then you can do failover on hot swaps and stuff like that as well. Okay, so much for Neo4j. Any questions so far for that? Okay. Let's look at Spring Data Neo4j. So you probably heard of Spring Data, which is the initiative from Spring Source to provide a easy and consistent way of accessing NoSQL databases from Spring applications, which has grown from its infancy in 2010, I think, when my CEO sat down with Rod Johnson and wrote the first implementation, which was actually Spring Data Neo4j. So the two CEOs wanted to do something productive and useful, so they got down coding, and that's what was kind of the birth place of the Spring Data project. And so the different Spring Data sub-projects support different NoSQL data stores and also relational database stores. So there's Spring Data JPA, there's Spring Data MongoDB, there's Spring Data Redis, there's Spring Data Hadoop, and Spring Data Neo4j. And what's really important is, unlike other projects, they don't hide the power of the database. So you have, for the common use case, you have convenient and consistent access patterns, like you have in the Spring framework in general, also like with GDBC template and so on. But if you want to use features of the database that make you choose the database, actually, right? Because you don't choose it because it, I can deal with it like with any other database. That's not the reason why you chose a certain database, right? So the really powerful features are still all available. You're not dumped down in what you want to do, but you're, the 80% stuff really is easy because it's kind of taken care of, and the 20% stuff, which actually makes the difference, is still available. As I already showed you, there's this really nice O'Reilly book which covers all the Spring Data projects, and it's written by the project leads. And it also has a really nice, consistent example project across the different databases. So we use the same domain and added some bits and pieces depending on the data store, but the core domain is the same. It's a kind of boring e-commerce domain, but we thought rather have people to learn about Spring Data instead of learning a new domain. And I mean, e-commerce, it's known to everyone. And I give it out tomorrow, this signed book. So Spring Data Neo4j, how does it work? It has an annotation-based programming model, so it's like you would do in your JPA application. You annotate your entities with certain Java annotations, and then it just works. It supports Spring Data repository. I will show you what it is in a few minutes. And it also supports the Neo4j special features like the Cypher query language and Neo4j traversals in different ways. And the indexing that I already mentioned. And as I already said, it's always possible to drop down to the core APIs as well. What's interesting about Spring Data Neo4j, different to Neo4j itself, it adds the notion of types in the database. Because Neo4j is schema-free, as I said, so there's no kind of general notion of a type right now. It will change in the future, but with optional types. But right now, Spring Data Neo4j really uses means of the database to store the Java type information. So if I have a user class in my application, this information is also stored in the database. So I can use that, for instance, to check if I'm really getting back a user, or I can look for users, or I can make sure that in this kind of network, I access the right things at the right time. The type projection is something we spoke about when the question came from types and classes. And so it's easily possible to project, for instance, a user entity to an employee entity, or to a citizen entity, or something like that. Or I can project an order to a fulfillment order, or to a logistics order in different contexts, because I then need different attributes and different relationships, and I don't want to create these huge customer objects or order objects which are 1,000 lines long or something like that, and cover all the use cases in a single class, which is really annoying and not really easy to work with. There's support with combining relational databases and graph databases in a single application with the same entities and the same domain model. And like any other Spring Data projects, it's also a template available that gives you access to the lower level methods as well. So back in the old days, like really 5 years ago or so, a pattern how to implement a domain class in Neo4j looked like this. Don't do that. Don't try it at home, right? It's a thing of the past. So you had a domain class, and then it was attached to a node. So you actually passed in the node to the constructor, and then all the property access was handled as read-through or write-through to the underlying node in the database. So the domain object was just like a thin object-oriented wrapper or typed wrapper on top of this schema-free lower-level constructs. As you can imagine, it's a lot of boilerplate code. And I even didn't show the stuff that's needed to handle relationships, which kind of blows up on the screen. So if you look at the same class in Spring Data Neo4j, it looks like this. I just have a single annotation. And I have this ID field, which maps back to the node ID in the graph database. And I have this field name, which is automatically mapped to the name property on the node. And if I want to index, that, then I just add another annotation on top of the name, and I could even say, okay, this name or this login or whatever has to be unique, and all this stuff is taken care of for me by Spring Data Neo4j. So it's really handy and quick to write your domain entities, to first store data and retrieve data, and actually make it easy to interact with existing frameworks or existing parts of your application that want to deal with POJO objects, right? So you don't want to kind of rewrite your whole application because you just change your database, and then suddenly all the other parts of your application have to accept node node instances or something like that. But you want to still deal with domain-level concepts like a user or a song or a product or something like that. And you also don't want to write all the boilerplate code that's necessary for the mapping stuff. So node entity is an annotation on a domain class, the domain entity. All the fields are saved as properties on the node, and all the references to other classes are saved as relationships in the graph database. It's interesting because the graph model is actually more powerful than the object model, because each relationship in the graph model can be navigated in both directions. So if you look at your object models, you only have outward references, right? So if you don't put in the backward reference in your object model, you can't navigate backwards. So you have to put in both. But in the graph database itself, if you go to the, as I said, low-level stuff, you can always navigate every relationship in both directions. So you don't have to create duplicate relationships in orthogonal or opposite directions if it doesn't matter in your domain. There are some domains where it's really important to have both relationships because they have a different semantics. So for instance, look at Twitter or so, right? If I follow someone, he's not automatically following me as well, right? It's different in Facebook. If I befriend someone in Facebook, he's also my friend, both ways. But on Twitter, it's really a different semantic relationship. If I follow someone or he follows me, right? So you can actually add either one relationship if you don't need more, but if you need the semantics of two different relationships, then you can, of course, add them as well. And you create them just like normal classes with new, and you can save them. And also the lookup mechanisms of Spring Data Neo4j will return these instances as well. So you don't have to get nodes and then convert them somehow into your domain objects, but you can instantly return your user objects, your order objects, your product objects from the lookup mechanisms. And there's another thing. As I said, relationships or connections are first-level citizens in the graph database. So they are really not a kind of secondary thought or an add-on or something like that, but they're really important, and that's why you can also represent your important relationships as Java classes, and they are connected to two nodes, one start and one end node, can have properties and have a type, and you can deal with them like that. So if you look at an example from this small sample application that I'll show you, it looks like that. So I have a tweet which has this graph ID. I have the tweet ID which is unique. So whenever I store a tweet twice, I can either choose to get an exception then or just get the original one back directly. I have some text which is automatically stored as property. This user is handled as relationship with the relationship type sender, so I don't have to put in relationship types if I don't want to. I can put in fetch annotations for ego loading. So when I fetch a tweet, the user is also fetched as well. And I can have other relationships as well. So for instance, tags, mentions, tweet sources like for retweets and so on. So that's all the model I need to have a really advanced graph model on top of that. The next really interesting part of Spring Data is something that came from one of the side projects of Oliver Gierke, which is interface-based repositories. I think most of you felt the pain writing boilerplate code for DAOs. So I have, for each domain object, I have to write a DAO with all the access methods, save and delete and add and find by something and then write all the SQL and so on. And if you look at other frameworks like Rails or Grails, where you have these finder methods where you can just take the finder method name and it figures out the correct SQL statement for the finder method name. All this goodness is brought to you by these Spring Data-based interface-based repositories. So what you do is just write in an interface You don't have to add some implementation. Put in some methods. You can either use these methods that are derived from the method name or annotate them, and then you're good to go. And the super interface for the repositories brings already lots of operations implemented for you. So like CRUD operations. In Spring Data Neo4j, it's also index lookups, traversals, spatial queries, and so on. And you can extend them by custom implementation. So if you want to add some domain-level methods to your repository, to your DAO, that you have to implement yourself, you can add it as a side implementation, and then it's merged into your repository. So it's kind of a bit like mix-ins in Scala or other languages where you can compose functionality by adding other interfaces or by implementing stuff on your own. And it looks like this. So for instance, I have a tweet repository, which extends graph repository of tweet. Just an interface, no implementation. I say find by tweet ID. So you remember here we had this tweet ID property. So we know this repository is for tweets. And there's a find by method with tweet ID. So the framework goes on, looks at the mapping information, sees, OK, for the tweet class, I have a tweet ID property. So I just generate a query that does look up tweets by tweet ID. I also see that it's indexed, so it can convert that into an index lookup automatically. And I have to put in like this, and then I can use it in my controller, for instance, down here, like this. And I can also annotate things which say, OK, I want to find, what's that? I want to find all the text that this user used in all his tweets, right? So I have a user that I pass in, which is my starting point. I find all the tweets by this user. Then I find all the tags that he used in all the different tweets, and I return the distinct set of these tags, right? So just a single query returns me this, and I can actually paginate the results so that I don't get all the 5 million tags back, but just a page of 10 or 20 or something like that. Yeah.
Is there a point where for instance, someone acting like a DBA could intercept this query and specify things like page size, how to look ahead so they can tune the query to the database and the data level?
Right now, there isn't. Usually, that's also not needed so much because these local queries that I talked about, they don't need so much tuning. What you can do sometimes is to restructure your domain to make some of the, for instance, intermediate hops faster. So that's a way of how you can deal with more complex things that you don't want to go over 5 hops all the time. You just create a new relationship between the first and the last element as a kind of in-graph index, which allows you to take shortcuts. And that's something that you do at the domain level or at the, like migration scripts or something like that. And right now, there's only interception for lifecycle methods like save and delete and update and so on.
So how's the performance of Cypher query versus the Java APIs?
That's a really interesting question. So.
Can you repeat that?
Oh, yeah, sorry. The question was, how is the performance of Cypher queries versus the Java API? So in the past, it was that the Java API was always faster. But in the current implementation of Neo4j, we changed the underlying architecture so that both the Java API and Cypher sit on top of a lower-level API. So in the past, Cypher had to go through the Java API. So it was, by definition, slower than the Java API. And now they sit on the same lower-level API, which doesn't create objects and doesn't do object churn and stuff like that. So the performance gap closes more and more. It's not as fast as the Java API yet, but we work on that continuously. And the nice thing about having this declarative queries is that you can always optimize the query engine without changing the code in the application. So everyone who uses Cypher will benefit from automatic improvements. If you write your own Java API-based approaches, then you have to tune them yourself to deal with things like that. And yeah, so it's getting better and better. And hopefully at some point we will be much faster than Java API. But we're not there yet. But it's kind of the 80-20 thing, right? So for 80% of use cases, Cypher is more than fast enough. And if you want to really kind of scratch out the last bit of performance, then you can go, for instance, write a server extension for Neo4j that uses the Java API to do a certain use case really fast, right? And that's just exposed via Jersey in a REST endpoint, and then you pass in an ID and get some data back, and that's.
So the production environment, you see both Cypher and Java APIs.
Yeah, so we see really nowadays most of the use cases are people use Cypher for the majority of the tasks, and then they have kind of one core feature of their product that has to be super fast and super efficient, and then they write a server extension that is, it's kind of like a stock procedure, right? So it's a server extension which goes away with all the overhead and just does the minimal thing, does also pre-computation and minimization of results and returns only the needed stuff. And that's the usual pattern that we see these days.
Can you refer to those server extensions in your app query
There's
application?
so Spring Data Neo4j also uses a Java REST binding for Neo4j, and this Java REST binding can consume these server extensions. In the end, these server extensions are just REST endpoints, so you can use just any REST or HTTP library to consume them after all. And there are some Spring extensions for consuming REST endpoints as well, where you can get automatic mapping and so on. Okay, that's what the repositories look like. And so that's all the code I have to write, just the interface, and configure that with the base package of the repositories, and I'm done. I get them injected into my code and can use them like that. Template pattern is a well-known pattern. I don't have to say too much about it. It's lots of convenience. It adds a kind of nice result handling API. So if you look at JDBC template, it has this explosion of methods just to take the different input parameters and the different results it can produce. And I changed it in Spring Data Neo4j to use just return a kind of query result object. And then on this object, you can say to list, or I just want to have a single result, or I want to project this to another domain entity or something like that. So it's kind of a fluent API on top of your core, which is quite handy. Okay, the sample app, I also already showed parts of that. So if I do the whiteboarding thing, it's just I write down either the abstract way of I have tweets with tags and users that post tweets, and tweets are tagged, and I can add retweet features and mentions as well. And I can have the mention thing here, for instance. And I can also do the concrete example on the whiteboard where I have people and concrete tweets, concrete text, and so on. Right? So I can do it either way. In the graph, it looks then like that. So for instance, I have Oliver here who tweeted. It was from, I think, from last year. Who tweeted something. Other people were mentioned in this tweet. Then certain tags were in this tweet as well. And this tag for Spring 1 also had 29 other tweets in this moment, and so on. You can imagine how this folds out to a huge graph.
But in this example, if you had to search a keyword, which is not that.
Yeah, that's kind of an orthogonal concern. So there are two ways that you can always do. Either you index the tweet text as in a full text index in Neo4j itself. So you can do full text index in Neo4j. But you can also say, okay, I want to integrate it because it's NoSQL and polyglot persistent. I want to integrate Solar or Elasticsearch with that, and then I just, while storing the tweets, I also index them in Elasticsearch, and then I do the full text search there and pull it in on the reverse. So I get the tweet IDs, for instance, back from Elasticsearch, and then do the graph stuff here. Right? So it's a common pattern that I use the technology that's best for a certain task to do it, and then find a good way to combine the results or follow on onto that. Right. Repositories. So tweet, we've already seen that. This is all the code used for importing a tweet from Spring Social. So we just get all the information, create the user as the user has a unique index on the username, it either creates it or we get it back. So that save operation here is a get or create operation. We create a tweet. We add dimensions and the tags by doing some regex parsing on the tweet text. We can add replies, and save the tweet. And that's all that's needed to build up the graph that you've seen here.
So when the last bit where it said tweet repository.save, is that when the whole thing's wrapped in a single transaction?
I put a transaction on the method. But the save method itself is also transactional. So in the definition of the CRUD repository, there's a transactional annotation on the save method. So it's also transactional. So you don't have to have that. But if you want to have the whole operation in one transaction, then you do it like that. So and then if we take this graph here and query it, we can do something like find me a tag, and then it was from last year's from the election, I think, and find correlations, and then we see people or tweets that mention both, which are really interesting, and then kind of text that come out of that. But you can do lots of other stuff as well. So the question was, which tweets mention Obama and Romney at the same tweet, and what kind of text do they use then? Okay, so much for the intro, to say so. Let's look at the some of the real-world use cases. So there are lots of customers. I don't want to talk about them, but rather about use cases. The problem with real-world use cases, yes, please?
How does it support pagination, like tweets or
Yeah, I think, did I have it in here? No. I show it in a few minutes. So the challenge with use cases is most customers don't want to expose their domains, don't want to expose their code. So I kind of extracted it and represented the domains. And I also have some open source things as well, where you can actually go to GitHub, clone the repository, and use them directly. So first example is a huge international airlines. You all know these entertainment onboard entertainment systems, right? So when I flew to the US, the entertainment system crashed, and they had to reboot all these things, which was really funny to look at, because all the screens were showing just Windows CE booting up and scan disk running and check disk running and so on. So they have all the media assets, and they have like hundreds or thousands of planes with thousands of movies and TV series stored on them. And the interesting challenge for them is first to find what is where, because they only have a number of licenses for each movie, for instance. They don't get kind of a free thing. Yeah? I know. Okay. So they don't get a kind of free-to-use license, but they get a license to use this movie 500 times or 1,000 times or something like that. So they have to manage their licenses. They also have problems with legal, also which movies can you show while flying over which countries, stuff like that, really crazy things. They have to figure out, so all the movies and all the stuff is on these streaming server boxes that they put in the planes, and they can rip them out and put them in another plane. So they have actually to track these boxes where they are, because the movies are physically on a box. So it's a kind of SSD RAID which streams to the whole airplane. So they do have to deal with permission broadcasting rules. They want to track what is where, have also virtual containers and so on. Want to document for their maintenance crews, if they take this thing out, in which plane do they have to put it in back and so on. Legal change, impact analysis, decision support, and so on. So it's a really complex domain model. I think they have like 50 or 100 entities in there, which is a crazy domain slide, which I didn't reproduce, but just a subset of that. Their technical setup is they use Neo4j embedded with advanced mapping, and use a Spring MVC REST server to talk to their web app, which is built with Thymeleaf. So they started with Ru, but were not so happy with that, and so they switched to their own implementation. And they have a rich UI which has all the CRUD interfaces, all the CRUD insert thing, But they also added a really nice dependency network visualization, so you can start from an asset and then see really as a visual representation where is this movie or this type of movie distributed in our network, which planes carry that. And if I have to withdraw this movie from all the planes, which crews do I have to call or to send them an email to do that, and so on. They can also navigate interactively in this network. And actually, for more advanced users, they even added a Cypher kind of query console where people can really type in either full or parts of Cypher queries and then get the results of this query visualized as well, which is really nice. So the domain model looks like that, but just kind of times 10. So this is really a tiny section of that. So you have movies, TV series, recordings, and things like that, which are stored on media boxes, which are installed in aircrafts. And the aircraft is on a route from some airport to another airport. So that's where the legal stuff with countries, flying over countries comes in. And the metadata is something like licenses, publication rights, all this other stuff, screen formats for aircraft types, and all the other things that they have. And it's all these connections are leveraged for certain use cases they do on top of this, domain model. So if I want to reproduce that, they have this abstract asset class, and then it's stored on a media box with this stored on relationship. The ID of this asset is indexed as well. The type could be, I think, the movie and so on. Genres, I can link it to a metadata, which can be one metadata instance or 100, depending on the type of content. Then we have the media boxes where we see, for instance, this stored on relationship is bidirectional, right? So we can use it from the asset to the container, or we say direction incoming on the other side, and then on this side it's a collection. And it's the same relationship in the graph, it's just navigated once in one direction and the other time in the other direction. And then a repository looks like that. I, for instance, want to find all the planes that have this asset on them, which is just a query to find the boxes, find the aircraft, return the aircrafts. Or have things like, find me all the assets for this genre. I missed to put in the parameter there. Another use case. So any questions to this airline use case? Yeah?
I had a question. Go back on the example there, you had the asset as an abstract class.
Yeah, so I think I wanted to do it differently, and then I didn't finish that. So you can do either way. Either you have a type entity, which is kind of a movie entity in the graph, or a TV series entity in the graph, and represent that. Or you can have just concrete subclasses of the asset, which are then stored in the same node, but have a different type information attached to them. It's kind of both are possible. And it kind of depends a bit on your use cases, what you want to support, and so on. So I was not consistent in this thing here. So another use case, it's kind of an interesting thing. I didn't think about this before I learned about it. So Junisphere is a Swiss company who does business process to IT hardware and software modeling. So, lots of companies run lots of processes, and they don't usually care what kind of IT infrastructure all the stuff runs on. They just run it somehow, and only if something breaks down, they call some IT guy, some admin, and also a sysadmin to fix stuff, right? But what they did, their business value proposition is to say, okay, you have all these business processes. They are really critical for your enterprise, for your company. Shouldn't you actually care what kind of service, what kind of hardware they run on? And shouldn't that be a kind of an optimal combination that you have always, all the capacities available that you need to run your business processes? You should be able to apply if you install new business processes, what do you need, who's responsible for what, and all the different things. And they build a suite that's not only the kind of top-down view that you usually see in BPM and so on, but they also have this whole systems monitoring, IT service monitoring, with agents and sensors from the bottom. and they meet in the middle where they say, okay, these high-level business processes are mapped to these technical processes. And that's a kind of really interesting challenge, because they have to map the two sides to each other, and they have to deal with frequent updates. And both the business processes as well as the kind of information networks from graphs that they have to map to each other, and that they have to continuously update it. So they get lots of new either delta updates into this graph, or full updates where they have to detect deltas. So they have to create graph deltas to apply them to their domain model. So there's also use case description there. So it's quite interesting. And they were one of the first Spring Data Neo4j users and gave me lots of feedback and contributed to the project as well. And that was quite cool to see them really use that. And we figured out some performance issues which we removed and so on. That was really good.
So as part of the graph update, can you merge the two graphs together?
They have all of them in one model. That's also an interesting aspect of graph databases, that you tend to put lots of different domains in the same graph database. And then the more domains you put into this graph database, the better the kind of questions are that you can answer, right? So because if you just had one, and then you have to go to another system with the information that you extracted, you lose kind of a lot of fidelity on his gateway, right? And if you put them both into the same graph, then you can also start to add new connections on places that you didn't anticipate before, right? So you don't have just a really tiny bottleneck of means of connecting the two worlds, to say so, but you can really leverage the whole graph model to connect them in lots of different places, and then have a richer model there. Okay. So, and they also did build an OEM application from that and converted a C++ application to Java. So they use Java embedded in Spring Data Neo4j and built their own XML editor, which kind of works for this business process stuff, and then they get these XML files back that they have to merge in. Same with the hardware scanners. That's one of their domain models. So they have services that depend on devices. Then they have integrated KPIs, both on the business process things here and on the low-level things, and lots of dependency tracking and impact analysis on top of that. And what they did, they looked at lots of different database models, lots of different graph databases, and then looked at their use cases from modeling, ease of modeling, to performance, to versioning support. So they added also versioning support on top of Neo4j, Spring Data Neo4j. They added multi-tenancy because they have multiple customers using the same backend, to say so. So they added multi-tenancy as well, and different view projections for the different use cases that they want to solve. And actually, it worked for them quite well, and they are happy with that, and so happy customer. So next use case, let me just see how much time we have left, and not so much. Next use case is a startup. Why own it? You know, modern share economies, we don't own stuff anymore, we just share it with our friends, all happy, big happy family. And this startup says, okay, why don't we just enable people to see what other people in their network have, what they could use, or what people in their location have, what they could use, and so on. And so you kind of match needs and availabilities. It's like a small market simulation, or a small market that you do, and location-based things. So a simple domain model is just have people who own things. Things have categories which can build trees. Some person needs something, but they don't need a concrete instance or a concrete thing, but they need something of a category like a hammer or a car or a boat or something like that, right? And then you try to match that and find something, preferably from people that are rated well, or that are in your friendship or trust network, and so on. And if you look at the code, it's I mean, the code looks similar, just apply to different domains, right? I mean, it can get boring. So something that's interesting is, so we have the thing here with the category and the owner and the current borrower. The category is handled as a tree. So we have a parent and a child attribute here, but which use the same relationship. So it's a tree in a graph. But at this concrete category, I have one parent relationship and a number of child relationships pointing from my children to this current instance. And that's all handled by that. So I just changed the direction between incoming and outcoming. Same relationship type, and I can easily handle that, which is really nice. A person is uniquely identified with its email. I have a trust network. I have stuff that I own. I have categories that I want. And I have perhaps rated other people. So this rating is interesting because it's not related to a relationship, but related to wire. And this is, the rating is a relationship entity. It's over here. So we have a start node person and an end node as a person. And then I can say, okay, this guy's hammer was really bad. I always hit my thumb with that, and that's why he only gets 1 star and stuff like that, right? So, and you build up ratings, and you can use that as part of your queries. A simple query is, I need stuff, and I want to find all the suppliers for all the stuff that I need, right? And what I say is, okay, I start with me, a person. I need something from this category. This category is has a thing in there. And then I find the owners for this thing. But I don't want to see these where this thing is already out right now, right? So I just filter that relationship out. Return the owners. And here we see how the paging works. So we can pass in a pageable instance, which could also be created from a HTTP endpoint like in Spring MVC automatically from page size and offset. And then I get back a page object, which is kind of a collection, which also contains page number, page size, total number of pages, and so on. It's also possible to add a count query here for the total page calculation as well. And the find by email is again one of these automatically generated finders that I don't have to do anything for. Okay, next use case is Gamesys. So they are a classical gaming company. So they do in the UK poker and stuff like that, really the money-making games. So they had a Spring web app with an Oracle backend. So they were a big Oracle shop. And they wanted to add social to their system. They wanted to add a referral system where you can refer other people, and then you participate in their bonuses and get stuff from them back. And they want to prevent fraud, of course. They want to have a multi-level buddy system where you can have a tree of buddies, the snowball stuff. And then they wanted to add more social functions on top of that, like groups of, like-minded people and so on. And there's a really nice video from the people presenting that at a conference and also at a webinar, what they did and what kind of things they had to get going. So for the buddy system, it's really easy. I have people who refer people, but only if the referrals actually come back to the platform and say, I was referred by this guy, they create this buddy relationship. And this can also be a tree. So for instance, this guy referred this one here, but as he went back and said, I was referred by this one, so it misses perhaps a reverse relationship here, he gets the buddy relationship there and not to this guy. So you can also compete for buddies, kind of, right? So people play rounds in certain games, and then you can infer, for instance, people that like the same kind of games and so on. Stuff like that. Music sharing. So there's a lot going on in recommendations, like with Spotify and Pandora and so on. But there's also other things, like I want to see fit out duplicates in my music network. So for recommendations, you look at listen history to favorites, look what it's hot amongst the demographics of this user. You infer stuff like he listened to this, and this was this band, and the members of this band also created new bands, and then so on. Yeah.
So, in the prior example, you had paging results based on I need this thing, and you can find a few.
Yeah.
Is there a way to order the results based on, say, ratings of that person?
Yeah. So you can say here I also pull in the rating of this owner, and then you say order by, after the return you say order by rating dot stars or something like that. Or you can also accumulate them, sum them up, or average them or something like that.
So in this example, in the, like in this one,
Yeah.
clear example, you mentioned that they were using a relation database before, and they decided to use Neo4j.
They added Neo4j.
Added
So they kept their relation database for all the other stuff, but to add the social features, they tried it with the relational database, it didn't work, and so they used Neo4j for all the social functions.
Right. So now if they have layers in both the relation database and the Neo4j, and the new players keep coming to the new platform, how would they keep the two databases?
So they keep kind of the master data of the players in the relation database. So all the details like address and age and all the stuff that you don't need for this kind of use cases, and they kind of replicate all the information that they need for the social stuff into the graph database, and some of the information like the buddy system is only in the graph database, right? So all the stuff that makes up the social part of the application is only in the graph database, and all the kind of master data kind of like thing is only in the relation database.
Do they replicate in real time?
Yes, yeah. They, I think they use a messaging solution, and then when messages of people joining come in, then they just split it out to the two databases at once.
So how do they guarantee that the two databases are the same?
There, I think they use something like a cross-store transaction, so XA. So there are lots of other use cases. Something I just want to show you is the open source projects. So for Spring Data Neo4j, there's this Cineas demo project, which is the social movie database, which is also part of the Spring Data Neo4j guidebook. There was one challenge in Boston. The Hubway guys, which is a bike network, published a dataset, and I wanted to import it into Neo4j. And I didn't want to spend too much time on that, so I just used Spring Data Neo4j to model the domain with bike strips and so on, and then it was just an easy way to push it in, and then you could visualize stuff like that. So it took me like an hour or so to model domain, push the data in, and then make it available to be used. There's also a guy who open sourced an energy market or a modeling tool with simulation from the University of Delft. It's also on GitHub. And it's also running on Spring Data Neo4j and simulates changes over time. It was quite interesting because he had some really interesting insights of energy usage, nuclear versus sustainable, and so on. To finish up, there are lots of ways of getting started with Neo4j. You got one of the best ways already in your book. And I'm almost done. Yeah. If you have time tomorrow evening, join us for the meetup. I want to speak about the future, where we will be going with Neo4j and Spring Data Neo4j, and probably some stories of the past. And Emil will be around, so he can tell the story of how he and Rod sat down in the hotel lobbies, coding, and so on. So thanks a lot for your time. Last few questions.
So if you have to have two databases that are physically separated for legal requirements,
Yeah.
how do you maintain your links?
So you can set up syncing means. So either you set up kind of an ETL process that syncs data from A to B. You can also integrate it with something like Talent and other ETL tools which syncs data from A to B. But there are also means, for instance, in Neo4j that you can add transactional listeners. So on commit of the transaction, you can call something in another database or update something in another database as well. It's also possible. Cool. Yeah?
Elaborate more like how compared to document database like MongoDB
I think we can take that afterwards. Just come to me. It's different data models mostly, but come here. We can talk. Yeah.
I just had a fundamental question, or maybe I missed this early on. The difference between a node entity and a domain entity.
A domain entity is kind of a projection of a node entity or of a node. So a node entity is just an annotation that says this domain entity should be mapped onto a node. But I can have 10 different node entities mapped on the same node. Then the different properties are stored on the same node, and I use it in different contexts or different scenarios. Okay? Yeah.
Question about the physical layout of the data. So the nodes and edges are stored in different files, right?
Yeah.
So how does it work so that the traversal in the graph is fast? So how are these files sorted somehow? Or how
It's a bit more involved, so we can talk about that later. But in general, the files are record-based, but it has a second-level cache that is kind of reifies these records into objects in memory, and then it does the traversal on the in-memory representation.
Another question then: how big is that cache normally? What is it the function of? Because I can imagine that if that cache does not fit into memory anymore, then your performance will fall.
Exactly. So exactly the size of this cache is your hot data set, your work data set, kind of the things that you usually touch in your use case. And if it's bigger than a memory, you can just set up a cluster and scale out and, for instance, say, okay, you route this geography to this machine, this geography to this other machine. So they have different working data sets, which then still fit into the caches. But it's also explained in the book, by the way. Yeah? Where? How far? This? Yeah, I upload them right after now. Thank you.